Welcome everyone. We're going to talk about drawing Lewis structures today. This should be a review from first year chemistry, but I'm going to make sure that you know what I think is the most efficient method to go about doing this. And just a reminder for why we're drawing Lewis structures. So when we look at a formula, we really want to understand how the electrons are arranged in that molecule. We know that it's the valence electrons that are involved in the bonding. And so G.N. Lewis proposed a relatively simple way of representing the atoms and those bonding electrons in a very concise, easy to draw on paper method that we call Lewis structures. So you've seen Lewis structures before, but let me point out some of the highlights here. So as you're looking at Lewis structures, you have both bonding electrons and what are called lone pairs or non-bonding electrons. The non-bonding electrons are shown as dots around the atoms that they are localized on, whereas the bonding electrons themselves are often represented as a line, and a line represents two electrons. So each line is an electron pair. So if I look at the molecule NH3, which is ammonia, that molecule consists of 4 atoms, 1 nitrogen and 3 hydrogens, and it has 1 lone pair and 3 bonding pairs of electrons. And hopefully you'll remember from first year chemistry that we can make single bonds, double bonds, and triple bonds as we see in carbon monoxide on that third structure down from the top. So let's get down to the nitty-gritty. Let's talk about how you're going to draw Lewis structures. I recommend what I call the NAB approach, which means you're going to begin by calculating the number of needed electrons to fill the valence shell of all the atoms involved. For most elements that we're going to work with on the periodic table, this is 8. The primary exception is going to be hydrogen. We'll talk about a few other exceptions in class. Once you've calculated the number of needed electrons, you're going to figure out how many electrons are actually available. That's the A part of the NAB. And you'll do this by looking at the periodic table and determining the number of valence electrons in each of your atoms. Once you have those two pieces, you're going to calculate the number of bonds necessary in order to complete the valence shell for all of the atoms involved. And so to do this, you're going to take the number of needed electrons, subtract the number of available electrons, and divide by 2, because there are 2 electrons in every bond. Once you've determined the number of bonds you need to make, then you're going to draw your atoms, add a skeleton of those bonds, and then go back and add the non-bonding electrons in order to fill the valence of all the different atoms. And when you go to add those non-bonding electrons, you're going to start on the outside atoms first and fill the central atom last. Let's take a look at 2 examples. The first of these is going to be carbon dioxide, which has a formula of CO2. To begin, you're going to calculate the number of needed valence electrons to complete the shell for both carbon and oxygen. So carbon needs 8 electrons, and each oxygen needs 8 electrons, and so I need a total of 24 electrons to complete the valence shell for these 2 or 3 different atoms. Next, you're going to count the number of available electrons by looking at the periodic table. Carbon has 4 valence electrons, whereas each oxygen has 6, so you have an available 16 electrons. Now we can calculate the number of bonds necessary by taking 24 minus 16, needed minus available, and dividing by 2. So you find that you need to make 4 bonds. Let's begin drawing the structure. In general, if you have one element that's different than the others, that'll be the one that is your central atom. But in a broader picture, your least electronegative atom typically goes in the middle of your molecule. So in this case, that's carbon. And then you're going to draw bonds to connect those atoms. Do you remember you have to connect all of the atoms involved in your molecule? The initial connection only takes 2 bonds. I have 2 additional bonds that have to go somewhere. Since this molecule is symmetric, in general, it's going to be best to be symmetric with your bonds. And so here I have carbon dioxide's core with its 4 bonds. Now those 4 bonds have accounted for 8 of our available electrons. We still have 8 more to place. So we're going to use those 8 to fill the valence shell of the oxygens first. The oxygen on the left currently has 4 electrons around it. It needs 4 more. So I will place 4 electrons around that oxygen that has filled its valence shell. The other oxygen needs the same, and that's actually used all 16 of our, that is used all 16 of our electrons. At this point, we should double check that we have satisfied the valence needs for all the atoms. The oxygen on the left has 8 electrons around it. The carbon in the middle has 8 electrons around it, and the oxygen on the right has 8 electrons around it. Remembering that when we're counting the number of electrons in covalent bonding, we get to count the electrons in the bond for both of the atoms that are associated with that bond. So at this point, our structure for carbon dioxide is complete. Let's look at one more. This is the nitrate ion, which has a formula of NO3-. Again, we're going to nav it. So we're going to calculate a number of needed electrons for the nitrogen and 3 oxygens. And then we're going to calculate the number of available electrons. Nitrogen has 5 valence electrons. Each oxygen has 6 valence electrons. But since this is a polyatomic ion and it bears a charge, that -1 charge indicates we have 1 additional electron. So I'm going to add an electron to the number of electrons that are available. This gives us 24 electrons, and we can calculate the number of bonds necessary by taking the needed electrons minus available electrons and dividing by 2. Here I have 4 bonds that need to be made within this molecule in order to satisfy the to fill the valence shell of all of our atoms. So as we start to draw this, let's put the nitrogen in the middle because it's different from the others and it's the least electronegative atom. We'll place our 3 oxygen atoms around that nitrogen. It doesn't matter where they go. And then we're going to connect this with a skeleton of bonds. At this time, we have 1 additional bond that needs to be placed. However, there are 3 different atoms that are bonded. These are all the same, so they are equivalent. It does not matter which one gets the double bond. We've used 8 of our 24 electrons that are available. Let's fulfill the valence needs of our oxygens on the outside by using those extra electrons. So there are 8 so far. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That has used all of our electrons, and we're going to double check to make sure that nitrogen has a complete valence as well. It has 8 electrons around it as needed. This Lewis structure is almost complete, but for ions, you need to place square brackets around your Lewis structure and put the charge on the outside of that Lewis structure. We will practice with drawing more Lewis structures in class, and we'll talk about exceptions to the octet rule, this idea that most atoms need 8 electrons to fill their valence shell in class. But hopefully at this time you'll be able to draw a basic Lewis structure by calculating the number of electrons needed to fill the valence, available, and determining the number of bonds necessary, and then placing those bonds and lone pairs around your atoms.